Sure.
Okay, so support, add structural interface. So the top section is, right, okay, this is quite important, both ends closed. So we want the first point, the top of the wall, to be open.
Yeah.
And
the last point closed, isn't it?
The end point to be closed. So both for the top wall, both ends open, I think, is the way to go.
Okay.
And we're going to install it at stage 2. Yeah.
Okay. Interesting. Wow.
So we're going to go and we can just type in. So it's 11.026. And we said
9.5.
6.5. 9.5, yeah, that's it. 9.5. Did I do wrong there? Okay.
No, I think
Control.
No, it's not 9.5.
It's going to be
13.5.
13.5.
Yeah,
13.5, yeah. Okay. Let's go again. So Control 7's a shortcut key. So both ends open. From there to 11.026 to 13.5. And I'm typing these in the bottom
in
this box here.
Yeah, I can see that.
So I just hit return and return again. So that's my first structural interface. So Control 7 again, and we want the bottom. Now here, the first point we want to be open and the last point closed. And what I mean by that is that the joints on either side can move separately. So at the toe of the wall, you don't want the joints to move separately. You want them to be tied. Probably is the way. You don't want the mesh to be able to separate at the end, at the toe point. Yeah.
So what do you mean by what is separating? Is it the soil from the actual pie?
Yeah, and sliding. So you know, the toe, you don't want the soil on either side of the interface to move separately. You want the soil to be fixed to the pile toe at the end there. Yeah.
Okay.
You don't want the soil to separate.
Okay.
I mean, you could do them both open, but I've seen problems with instability happen when you do that, and you see some weird effects. Okay, and again, install at stage 2. Click on OK, and just draw this down to that boundary. Okay. Right. Now you've now got these 2 structural interfaces in there. What you can then do is you can assign different properties. So what I'm going to do in the first instance, structural interface properties. I don't know if you've got actual real parameters for these.
I would have them.
If it's for
but it's for an example. Don't worry. I think it's
okay.
It doesn't matter.
Okay.
It doesn't have to be. I just want to know how to do it. And
yeah. Okay. Well, let's just copy this.
It can be the same.
Yeah. Okay. So config pile wall. So if we go to, I'll tell you what we'll do. In the properties, define liners. We've got config pile wall. Hang on a second, what we've got here. Properties, define structural interfaces. We've got the top is config pile wall, and the bottom is going to be. We want that to be a liner 2. Okay. Okay. So I'm just going to change some of this stuff. We've got that liner 2. We're going to say bottom liner. And I'm going to call this a top liner. So this is just the top beam, if you like.
Yeah.
And you've got different options here. You have geosynthetic, reinforced concrete, cable truss, but just stick to standard beam. Yeah.
And okay.
Okay. Okay, so we've got the we've got these 2 structural interfaces now, and what you'll see is that both structural interfaces have got joints either side. Yeah. Now, again, we've got a choice of multiple joints. We can assign a different joint to each side of the interface. But what I'm going to do for this example, I'm just going to use the same joint for all interfaces. And what I'm going to do, I'm going to choose the slip criterion for the joints to be 0.67, and this will be 0.67 times the weakest material. So the soil, 0.67, 67% of the soil shear strength. So if you've got a friction angle of 30 degrees, it'd be 20 degrees. Yeah. Now you might want to play some tunes with tan phi, but for the sake of this demo, we'll just make that 67% of the soil shear strength, and the stiffness will just make it the same as the material stiffness either side of the interface. Yeah, so we'll just use a material dependent stiffness, material dependent strength. We want to apply pressure to the joints, pour pressure to the joints, so we'll just leave that box ticked by default. And at this stage, we don't want to stage the joint properties. Okay.
So is this the joint between the element and the soil?
Yeah, so this is the joint between the structural beam and the soil. Okay. Now, these joints are represented by springs. So the beam elements are tied to the soil elements by springs.
Yeah.
There's a shear spring and there's a normal spring.
Yeah.
Okay. So we can do that.
What about the connection between these 2 liners? Is it by default fixed connection?
I think it's a fixed connection by default, but we've got let's run it and see, because it'll become immediately apparent once we've run it.
Okay.
So we then upfill, and I just noticed there's a slight error with that now, because I just need to excavate that material. And then we apply the surcharge. Okay.
How do you excavate? Sorry.
So we upfilled. When we upfilled, I don't know if you noticed, this fill material, this made ground, has gone from being a made ground material to the 6F2 material.
Yeah.
So again, in properties, assign properties or Control A. You can, same as slide, you can assign different materials. You can call this that. We want it to be 6F2, or if we want to excavate a material, remove a material for a given stage, we just click on the excavate.
Yeah, I never saw that excavate. At least I didn't see it in slide. I don't know if it's there, but I didn't see it.
It's not in slide.
Is it not? Okay.
Excavate isn't in slide now.
Okay. Cool. Yeah. Thank you. That's good.
Why is that not? Yeah. Let's come back out of there a moment.
Yeah, well, if we just put it on them, that will need the engineer to
Control A. Control A. properties, site properties,
Yeah.
materials. 6F2.
Yep. Thank you.
Okay. So stage 1 is just analysing the slope. It's an existing condition. Stage 2, we I don't know if you saw the colour of the wall is kind of a faded colour.
Because you say assign it to stage 2.
Yeah. So hang on.
All the drawings clearly show very prompt.
Yeah.
Every like this.
Install at the stage, right? Yeah. So the wall is showing as a faint colour. Sure, it's in the model, but it hasn't actually been installed yet.
Yeah.
When we click on stage 2, the wall changes to its sort of fully opaque colour.
Yep.
We've added the fill material, and then at stage 3, we impose the surcharge loading. Okay.
Yeah.
I'm going to turn off the shear strength reduction because that takes a little time to run. So what we can then do is we can just mesh the model. And as I say, we've used a fairly crude, or I used a fairly crude discretization to start with. And we can just run that then. Let's see if I can just mesh setup. I had graded, discretize, and mesh.
Well, it started.
It's crashed.
Oh, right.
Yeah. It's a shit
Was
show.
it?
Then we waited 8
Yeah,
weeks
it's
for them to
bombed out.
And they're like,
That's not good.
That's not good.
You got something closed, small there on the left
No,
hand side. No.
it's crashed.
It's something what they're doing, what they're delivering. Who's taking design responsibility for
Well,
it?
look, let me show
It
you.
doesn't matter. It doesn't matter.
Yeah.
I followed the just
Yeah.
just do your run and
Yeah,
It doesn't-
that's
it's
first
not a
time-
problem.
That's the first time that's happened. Well, look, let's have a look at the results. What I did was I modelled this using I've done a shear strength reduction analysis. So I've got these 3 stages: initial, apply the upfill, or I upfill and insert the wall. I then put the surcharge on. I then march through this shear strength reduction analysis. Yeah. So if we look at the slope, it's in its existing condition.
We're not sending
Then look at the maximum plastic shear strain. There's no failure. The model converges. There's no failure mechanism developed. So in its existing condition, the slope is stable.
yeah. So because there's how do you read that? It is stable. It's because of the numbers on the left.
Well, for a start, the model is converged. Yeah.
How do you know it's converged? How do you know it's not converged?
Because it, if we look at the where is it? Edit? Where is it? File. Where do I get it from? No query, analysis, log file. Okay. So if we look at the log file, so stage number 1, it's telling us that the model's converged. When it fails to converge at load stage, this one, right?
Conversion may not be established.
Yeah. So we get this warning in the log file here when we've got shear strength reduction factor of 1.05. We've got a warning that the final load step, blah blah blah, convergence may not be established or problem is unstable. Yeah.
Oh no!
So we've hit the iteration limit of 500. If we increase that, we might get to a converged solution. but for all the analysis stages prior to this stage, the model is converging. Okay.
Yeah.
They're going there.
Thank you.
How many rigs are going there? 2? 2 and mini rig.
1.
Thank you.
Blast, I put it down. Okay, so it was model number 506. Right.
They were trying to win the job.
I haven't heard anything in a while. I don't even know it's still.
So model number 5, we'll go to the, load up the interpreter again. Okay.
Guess where we're busy, it doesn't really feel like the market's quite quiet.
So I'm going to just reset the stage settings.
I think you had the number 6 before open. Another 5.
Sorry.
Was it number 6? Okay.
No.
Yeah. So this is model number 5,
Okay.
where I've actually used quite a crude step in my shear strength reduction factor. I've basically gone from a shear strength reduction factor of 0.9 all the way up to 1.6, and you can see that as you increase the shear strength reduction factor, you see a low shear strength reduction factor. You've got an active wedge forming on the retained side of the wall, and once we get to a shear strength reduction factor of 1.05, we've then got a failure mechanism developing right through the model. And the other thing you can look at to help identify that is if you look at this graph of shear strength reduction factor. This is a plot of maximum displacement in the model against shear strength reduction factor, and you can see that when you've got a shear strength reduction factor of 0.9, 0.95 and 1, the displacements are pretty much constant. There's very little change in the displacement. As soon as you get up to 1.05, and going from a shear strength reduction factor of 1 to 1.05, there's a much greater change in displacement. Okay. So you know that your safety factor or your shear strength reduction factor is somewhere in that range.
So it sorry, maybe this is I don't understand this shear strength reduction factor. Is that equivalent to the factor of safety?
Yeah, it's exactly equivalent to the factor of safety.
Okay.
So you're just dividing tan phi by your shear strength reduction factor, and you're dividing C by your shear strength reduction factor.
Okay. Understand that.
Now you can do that manually by staging the properties. So for each stage, you can factor your strength parameters, and you can factor your loads for different stages. And this is quite useful because it enables you to replicate the Eurocode 7 design approach, whichever design approach and load combination you want to go for. So in the UK, it's design approach 2, load combination 1 and 2, I think, isn't it?
Design approach 1,
Yeah. So you can replicate that pretty easily, and I can show you how to do that. But
that would be very useful. Yeah.
Just starting off with this, this is a useful thing to do because it gives you a feel for your problem. We're not factoring the loads; these are unfactored surcharge, and then we're automatically just stepping through and increasing the factor of safety. And this kind of replicates your multimodal analysis in slide 2. You can see different shear bands starting to form. You've got one starting to form up here. And ultimately, you've got a global failure, and you can visualize that this failure mechanism in lots of different ways. These are displacement vectors. Wow. So these are nodal displacement vectors. You can, instead of contouring shear strains, you can contour various components of displacement. So if you just want to, let's look at total displacements first of all. So again, I'll tell you what I'm going to do as well. I'm going to just set the stage to 1 because I want to take out the movements that develop, the in situ. So that's our starting point. Yeah. So when we upfill, these are the additional displacements we see. Add some surcharge. We see this. We then drop the factor of safety to point, or the shear strength reduction factor to point now. And what we should see now is that these displacements will start to increase. So you can see that as you go from a shear strength reduction factor of 1 to 1.05, you start to see displacements all the way down the slope face, and you can change that to horizontal displacements if you want to. You can change it to vertical displacements, solid displacements, vertical. And this is where you see a discontinuity in the displacement field either side of the wall. And this is where the joints are doing their thing. So they're letting the soil move downwards on the active side of the wall. You can see you've got a little too. I'm going to do. I'm just going to change this contour options lines only. Okay, so you can see that your downward displacements on the active side of the wall are much greater than the downward displacements on the passive side of the wall.
Yep.
Which is what you'd expect because you've filled here. That's causing the soil to compress and settle behind the wall. On the passive side of the wall, you are still seeing some downward movement as a consequence of that in response to that load, but it's significantly less than the downward movement on the retained side of the wall. But the big advantage of this is that at working load, what you can now get is your bending moments in the wall.
Okay.
Yeah. You can get your shear force diagram in the wall, and you can get your axial force in the wall. So this is per meter run of wall.
Yeah.
So you obviously need to, divide by the pile spacing, or multiply by the pile spacing. But you get this information out of the analysis.
Yeah. And then you can bring that directly to design that pipe straight away.
Yeah, exactly. Now you can't do this with any other. I'm not aware of it. The equivalent Slide 2 stuff that you get. Okay, you can get fairly similar results. So this is your Slide 2 model, and I've just done a multimodal analysis on this. So I'm getting factors of safety. Well, the shape of the failure surfaces is somewhat different. It's a different model, obviously. You're not accounting for the interaction between the pile and the wall. And all you're doing here is you're just shoving a bit of extra resistance in, shear resistance in from the pile, which isn't really I don't think that's a particularly good model of the pile. And the factors of safety that it's coming up with are quite a bit higher than we're seeing here. And it's not giving you moments or shear forces or axial loads in your piles. You've then got to go to Wallop and iterate between the two programs or some other pile analysis program. So it's a bit of a hack. This is quite a good way, I think, of designing or modeling the response of the slope to the installation of a contig wall, because it gives you everything. It gives you factor of safety on the slope, it gives you the moments in the piles. Let's just save this as, not this one, the model file. I'll show you how to, this was model 5, wasn't it?
Yeah.
Okay, so I'm going to save this as file, save as demo. And I'm going to take out the, oops, what have I done? Too many things open. Right, okay. Let's close some of this stuff down because I get horribly confused when I've got so many things open. That's 6. I'm going to close that one down. This is, what have I got on here? Move that out of the way. Right. Okay. So, what have I got? I've got this. This is the demo file. So at the moment, I've got the shear strength reduction analysis turned on in project
show me
settings.
How do you set that up?
Okay. So strength reduction. So let's start at the beginning. So in the analysis, it's similar to Slide. A lot of the settings are in project settings, and we've got this option here at the bottom of the list of shear strength reduction. Now I've got it turned on at the moment. I'm saying, okay, I want to start at a shear strength reduction factor of 0.9. I could have let it do its own thing, but I've chosen to say, okay, I want to go from 0.9 to 1.6 in steps of 0.05. And that was because I wanted to cover quite a large range of shear strength reduction factors.
And again, you're saying you're going from a 90% utilization of the slope step for so to speak.
Yeah, 90% utilization to 160% utilization.
Okay.
Yeah.
Fantastic.
Yeah.
Well, I'm probably you were gonna show me, but how to know what is the factor of safety of, for example, my wall slip. How do you? Because there's a lot of slips that I know it says 1.05, but there's different colors when you.
Yeah, the only way to do it really is to go through. I mean, if you look at the plastic strain, this is quite a good way to show. Just turn the color bands on again. Contour options, filled. Set that up to 60 because that shows it a little bit better. Turn off some of the clutter, and we can visualize this sort of on the deformed mesh. You start to see some slightly funny things happening on the interfaces. These are sort of minor numerical issues, but you get the overall sort of picture. I'm just going to turn the bending moment diagram off. So you can start to see you can display this as a deformed mesh, and I can turn off things like the boundaries. Okay. Right. So in terms of identifying your failure mechanisms, the model is converging. So up until 1, the model converges. Yeah. You haven't got a continuous. You can't see. This is plastic shear strain that we're looking at here. Yeah. So we can't see a slip surface or a shear band forming all the way through the model. Okay, you've got an active wedge, but the model is stable. That active wedge is being supported by the wall. Yeah. You've got active pressures in the soil behind the wall. Doesn't take a lot of movement, wall deflection, to mobilize those active pressures. That's not a failure as such. You just got active conditions behind the wall. Yeah. when we reduce the shear strength a little, we don't have to reduce the shear strength by much, however, to trigger a failure. Once we apply shear strength reduction factor at 1.05, so all we're doing is dividing the C dash and tan phi dash by 1.05, we can then see this shear band forming right the way through the model. Yeah. So we're seeing failure happening all the way down. Now again, if you go to graph and plot the shear strength reduction graph, you can see that the displacements in the model start to take off at this sort of level. And there are some jumps in this graph. So again, you've got things continue pretty much on the same line until 1.15, and then 1.15 to 1.2, you've got a jump, and 1.2 to 1.25. So you can then go back to this and say, okay, well, what's happening between those two? So we've just got more of the same in going from 1.05 to 1.1. And then when we get to 1.15, we can start to see another shear band forming here. This one's forking a little bit. Yeah. And then at 1.25, the failure mechanism passes beneath the wall. So you've got shearing and a slip, basically a slip surface forming that is passing beneath the wall once the shear strength reduction factor gets down to 1.25. The wall, by the way, I've modeled as elastic. So one of the checks you would have to do is, do these bending moments. Can they be carried by the wall? Can the wall actually support those moments?
Sure, that will be designing my wall basically to those moments.
Yeah, that would be a simple check for you to do. Is can the wall, and essentially your moment is probably highest at the working stress once the thing starts to move. So it's 150 and it jumps up to 175, but then once it starts to move, you should find that the moments will drop off because you get a loss of support. So what you probably want to design this wall for is a moment of 175 kilonewtons,
which is when
kilonewton meters.
Which is that. So this is.
That's per meter.
No. This stage we are 1005. So this is when the thing starts to fail.
Yeah.
So you will design. So your factor of safety here would be 1 divided by 105, isn't it?
Yes.
So if I design to this situation, I just don't see it very well. So now in this situation, the wall has failed. So this moment is it realistic?
Well, the wall hasn't failed because the wall's elastic.
The slip has.
Yeah, the slope I think has failed. Yeah.
So in order for me to avoid this situation, does the wall need to be that strong, or is it enough to have the 150 that I had before? Sorry.
Well, personally, I think you probably need either a longer wall or a stiffer wall.
Okay. I just can't see. So, for example, you're saying that the wall we are installing now, that with those whatever we put there, because it wasn't to any, we didn't design it now. So this is failing basically.
This is failing. Using this model is failing. Now, whether the model is representative, whether the parameters that you've used,
they're not. They're probably not. So So, I guess my question would be one: what it looked, how does it, what would it look something that is not failing? So, how would it? What do I need to see to say okay, this model is stable, it looks fine, the wall is avoiding preventing those slips? How does
Well,
it
at working load or shear strength reduction factor of 1,
Uh-huh.
the model doesn't fail.
Okay.
Yeah, but if you start to reduce your soil strengths, then you don't have to reduce them by very much. Say you're dividing C dash and tan phi dash by 1.05, you then trigger a failure. Now, I think that a large part of what's happening here is you're putting a bloody great load by how much fill is this? 4 meters, is it?
4.5, yeah.
Yeah, you got 4.5 meters of fill
Mm.
at the crest of a slope, and that is triggering this failure. Now, whether you can shield the slope from this load by deepening the wall and stiffening the wall, I don't know. I mean, we could try that quickly.
Yeah, stiffen it, for example. Say that's the depth, and if we make it, I'll give you the values for the stiffness.
Yeah.
And see what it gives.
Just give me the value for the below, the pile stiffness,
Yeah.
the below ground bit, because
Yeah.
I've only got a single.
I'll give it to you. You can see so the width is 450 and or the diameter is 450, and I think if I'm using this one, so 18,375 meter to the fourth.
So diameter equals 450 mil.
Yeah.
Right. So I've got diameter of 450 mil, and area. What is it? Let's function. Okay. Moment. Area. Help.
I can give you the moment of inertia.
Yeah.
I've got everything.
Yeah, go on. What is it? Moment of inertia. Okay. Right. Okay. So it's just moment of inertia. Disk. Do it in meters. Right, so 0.32. 0.32. Right, so that's our moment of inertia. What's the spacing?
I go per meter 0.002. The second moment of inertia.
What's the spacing though?
It's
1.6 was
1.6. Yeah, this one is 1.6. Yeah.
Okay, so MI moment of inertia. So MI divided by spacing.
Oh yeah.
0.02. Is that what you get?
Yeah. 0.02. Yeah, exactly that one.
Okay, so if I just file, save as. Moment. Where am I going to save this to? Because I've got this. so that's our MI per meter. Okay, so if we go into our structural interface properties thing, we should be able to change this. So we're going to change this to area, and our moment of inertia is going to be 0.02012. It's probably a bit keen. And the area is going to be so area of that is, but then we want to go area per meter is, that's per pile, but they're spaced at spacing, isn't it? Divided by spacing. So
can you change the moment of inertia to 0.002? I think is you need the second moment of inertia, so it will be another 0 there. That's what I'm getting. It's 2.1 divided by 1,000, which is 0.002. Yeah.
No.
Yeah, 0.002.
Diameter,
Yeah.
yeah, actually, yeah, because that should be divided by 2, shouldn't it? So the radius, radius should be radius. Sorry.
Is it not because this is we're looking to the second moment of inertia? Yeah.
Yeah, 0.002. Yeah.
That's it. Yeah.
But what we want to add into here, because we've got to divide it by the spacing, it should be that. Yeah.
Okay.
Yeah.
Yes, that's very good. Yeah, that's very good.
So if I bring that back up, then the area per meter, but all right, rad, that wants to be divided by spacing, so that'll be 0.999. So the area. Okay.
Of course, it's odd.
So Young's modulus 2.8.
No, we normally use. Yeah. That's what exactly.
Poisson's ratio 0.15.
That's really
We'll
helpful.
model this as elastic. We don't want any of that. Stage properties. We're not going to stage the properties for now.
But we could do it. Okay.
Okay, so we've got realistic
If we Google it.
parameters in now for the pile.
Yeah.
Okay, so what we're going to do.
So I didn't catch when. How did you jump from putting the model, importing it to here, putting the interface of the liner, then you do the meshing, and then you do. How do you do the SR? The what do you call it? Strength reduction factor. You go there, you do that, and then that
Project
does it automatically.
settings.
You do that. Yeah, I've seen that. It does it automatically. Then when you analyze, when you compute, it does it.
If you pull it in from Slide, this is automatically ticked. I'm going to untick it for this because what we're going to do, you record. We're going to add a stage in. Well, I'll tell you what. Let's just run this and make. Let's put the stage in now. So stages. We're going to put a EC7 design approach to LC1. Yeah.
It's actually it's design approach 1, but it doesn't matter. It's design approach 1 combination 2, but it doesn't matter.
Sorry.
Just,
Yeah.
it doesn't
I
matter.
get
Leave
so
it.
bloody
Yes.
confused. Now let's change it. Design approach 1. Did you say?
Yeah,
Load combination 2.
Exactly.
So we're factoring the loads and we're factoring the
Well, we're factoring down the soil properties, and we only factor
and
the
the
variable loads.
variable loads. Yeah. So the surcharge. Yeah.
Yeah.
You wish. I'd say you.
Okay. So we've got that in there now. So we've got this surcharge.
Very quiet.
So what we're going to do,
You wanna know how to play?
No.
if we look at the
No, just have that with me. Just it's
loading
so
tab here,
so quiet.
we've got this distributed load, we've got surcharge, and we've got the stage factors. Yeah.
Interesting.
So is it 1.25?
1.3.
Factor the
1.3.
1.3.
Yeah.
Okay.
Like a star.
I've got to. I don't do this every day, so I forget the bloody numbers.
I do them
So
every,
we
I do every day. I also forget it
Yeah.
sometimes, so it's confusing.
So
So,
so we're going to factor those loads by 1.3 at
Yeah.
load stage 4. Yeah. So if we look at load stage 4 now, we can see that the load, that surcharge load, has gone from 2.5 to 3.25. But we're also going to factor the properties for.
Yeah.
So we're going to look at the stage factors. So everything's factored by unity, and what we're going to do is at stage 4,
It's an expensive fence.
what do we factor by?
So
It's 1.25, isn't it?
I think it's 1.25.
Yeah, stuff like that's fiddly.
Yeah, I should have it. Yeah, I think it's 1.4 for the cohesion. I'm not sure, but it's 1.25 for the friction angle. 1.4 for the cohesion,
Yeah.
which is I think the most important. Let me bring it up very quickly.
0.8.
Yeah, exactly. So if
Yeah.
you do that, yeah.
So I'm going to.
You use
What-
1.8.
what-
0.8. You use 0.8.
I'll just
I
use
can
0.8
change it.
for every.
I
Yeah,
can
yeah.
change it later, but it's just good. It's a good to see it.
Okay. Now again, this should be factoring tan phi, but I'm not going to do it because I'm just going to.
Yeah, well, so far it's a lot.
So if we say
Essentially put the model in, so I've decreased the sheet length 2 meters
cohesion
above where we've told it.
0.8,
Yes.
dilation angle, it's 0. We've set that to 0 anyway. Again,
The
friction
model
angle residual,
based
just
on
make these the
axes at the
same.
bottom of sheet, leaving the anchors in their original position. And it is all okay.
We haven't used any of these things, so reset yield, no.
That is
Unit weight, we're not changing.
No.
Yeah?
No.
Okay, so I'm going to copy that line if I can. See if I can do this. I don't know if I'm going to be able to. Sort of dangerously.
Not that dependency, it's
So-
different.
I just want to see just the models in here. So we've factored the 6F2. We're going to stage, factor stage. We want to add a stage, and at stage 4. And again, I just want to see if I can.
It's not that.
Yeah, that works okay. $8, stage factors, add a stage, stage 4.
So what is he gonna do in stage 2 and 3? Is he gonna follow 1, or what? Is he just not gonna do anything?
Just 1, yeah.
Okay.
If from stage 1, 2, 3, it just nothing's changing, and then from stage 4 onwards. So if we had additional stages, it would be,
Then from the
You
Point
wouldn't have to do it for each stage afterwards.
no.
great.
It's just from this stage onwards. These are the factors that get applied.
Perfect.
Yeah. Add stage 4, and then
Depends what the options are. the top of my head, you want to, whatever you do, you're going to have to do it as if you're doing under
Stage factors, add
underpinning,
stage,
because if
stage.
you just dig out all of
Four.
that, there's nothing holding this up. It's just going to fall. I can imagine. Yes, you've got the anchors, but it's not really their job to have to deal with all that, is it?
And then the final one,
You have to do it in sec.
stage factors, add stage. Let's just see how I can
You
make this.
you wouldn't need that
bigger.
one anyway.
Where
You don't have it.
So that wants to be 4. And then just grab hold of that lot. Yeah, I'm just going to
whether we
quickly
change
run
whether
through
we
these
put
and
in
check
some
that it's
sort
all
of
got
concrete
stage
lining
4.
and then we install a nail through that.
Check they've all
and use
been
that
done.
as the facing.
Okay. Right. Save that now.
Yeah, save it before it
Yeah.
goes.
So
Yeah.
so now if this works now, this model should be stable at these loads. Now what you can do, if you were feeling keen, you could incrementally, let's say in, I don't know, 5 stages, incrementally increase the load, and by a factor ranging from 1.0 to 1.4, and incrementally decrease the shear strengths in the soil. We're not going to do that here. We're just going to hit it and see if the model remains stable. Now, if it does, then your design satisfies Eurocode 7. What I would probably do is I would want to know by how much is it satisfying it. So I might want to increase these factors on load slightly.
That's the only way. That's the only way you can know that.
Yeah, you can just increase these factors a little bit. So instead of applying, you could incrementally do it. You could add other additional stages, yeah, where you're approaching and exceeding the Eurocode 7 factors.
Yeah. Okay.
Yeah, because it's useful to know. If I was a designer, I would want to know, am I just satisfying the designer? Have I got plenty left in the back pocket type of thing?
Yeah.
So that's done now, and we should, in theory, be able to run the model now. It shouldn't take too long to run this.
I remember when we did this course. Sina used to create a box on this RS2 to do the strong, the slope analysis on that area only. Is that the same as strength reduction, or is it something else?
Yeah, that's it. That's what we're doing here. Now, I could apply a box if I was confident that, if I had a big model and I was confident, either confident that the instability was confined to a small region, or I was only interested in a small region, then I could define a box and say only do my shear strength reduction in this region. But for a smallish model like this, and because I want to know where my slips are going to be, I'm not going to mess about with that. It's really useful on some of these really big open pit models.
Yeah, this is nothing compared to some of the.
No, I mean this is quite a small model now.
Yeah.
Looking at this, this doesn't look like it's converging. So I think this model isn't satisfying the design requirements of Eurocode 7. So if we look at go to the interpreter, I'm just going to shut this down for a moment.
Thought it was preliminary, but this is like an actual
So
released.
if we go to the interpreter now, and it tells you here that it hasn't converged at stage 4. Yeah, so immediately that there's a non-convergence issue, and it says, do you want to view the log file? You can either say yes or no. If you say no, you can view the model file later, but we can select it here and we can go down to stage 4 and we can see it. This is just the information for each load step at stage 4. And at the end here, you get this warning.
That could cause issues with the ones that nailed.
Mm.
Drag the whole thing, wouldn't it?
Okay.
Okay, so this is now our slope model. What we're looking at here is a major principal stress at the in situ stage. We upfill, we apply the load, and then we apply the Eurocode 7 safety factors. So if we look at the plastic strain,
Unless
you've got this slip surface happening here. Now this is this becomes interesting because this slip was happening anyway. So what it may be telling you is that this may not be a problem.
Yeah, that's what I was gonna say. That we're not really too bothered about what happened in front of the wall.
Yeah, so you could say, well, okay, I'm not bothered about that. My design passes because I haven't got an overall failure mechanism developing. Yeah, this is just a local slip that would have happened anyway if you without the wall. If you just took the wall away, if you go back to your slide model,
Where's the slide
interpreter gone?
No, that's how I read it.
Why would you not say a trial pile diameter should
So
never be
you were seeing that slip happening
less than half of the working
anyway.
diameter.
Yeah.
That's just
Yeah, but this one is saying it's
So
1.14. So it's not really happening. It's stable. It's more than one.
Yeah.
More than one.
And it doesn't happen at working loads. Yeah.
True.
So at the working loads, it's not happening. But once you apply the Eurocode 7 factors, then you trigger this instability here.
Mm-hmm. Perfect. So then,
Now,
did you say there's no case working?
yeah. So again,
Bending
if you were to look at your bending moment diagram,
quite a lot. 300.
yeah, that's 352.
Mm-hmm.
That's with the Eurocode 7 factors applied, but the working load, 150.
Wow. Yeah, it does. It does when you apply combination 2. It's crazy.
Yeah. So, but would you design your piles for that?
There is a discussion in Eurocode 2. It says you have to check for both. If you use combination 1, you will have maybe 200 kilonewton or something, or maybe 210 or something. But in combination 2, it gives it twice as much sometimes or more. And we have the discussion internally, and we're not sure what to do. Some people could argue. Some people could argue that you have to do combination 2. But we're starting to use combination 1, and for the global stability, and then just for the piles, you just use combination 1.
I just think the Eurocodes are stupid.
Yeah.
I mean, you got to you factor your strengths, you factor your loads. In the old days, we just have a 1.5 as with unfactored loads, 1.5 on C dash and tan phi, and things used to stand up. There was we didn't used to have problems with it, and you could understand what's happening. But this is just crazy. I mean, that's a huge difference.
Yeah.
Yeah.
That's crazy. Fantastic. So that is really it, isn't it? We can
That in a nutshell is it. I mean, what I would say with RS2, it's really useful. There's a bit of a learning curve, but once you've got the program and if you start to use it, you get all your results out of one analysis.
Yeah.
We're doing some work at the moment, some collaborative work with Geosolve, comparing the results of RS2 and Wallop, and we're seeing, for basic cases, we're seeing really close matches. Things do start to diverge a bit once we get into more complicated scenarios, but that's because the two approaches, Wallop has got some fudges in it. The differences aren't that massive, but for basic cases like a cantilever retaining wall, we almost see a totally like for like comparison.
Is that without taking into consideration a lot of slope stability things, just analyzing the wall, basically?
For something like this, Wallop kind of isn't really well suited. I mean, you can put berms in there and what have you, but they're fudges. They're not they're not rigorous in the way that a finite element code is, where it properly represents the geometry of the slope.
It's more. This one would be closer to the closest thing you can get to reality, isn't it?
Well, provided you use sensible numbers.
Yeah.
You've got to have, you've got to use sensible numbers in it. If you don't, then it's the same old story, isn't it? Garbage in, garbage out.
Yeah.
But provided you do something sensible with it, you tend to get sensible results.
Yeah, there's so many options, so many variables, like you said, the sliding, whatever, between the soil, and there's a lot of things that you could just have wrong, basically. The interaction between the material and the soil, or the element in the soil. You explained to me, but
But I mean, again,
so that's
excuse me. There's not the problems tend not to be massively sensitive to those numbers. The passive resistance can be, but active pressures tend not to be. Your passive resistance does increase as the wall to soil cohesion increases, but that's what happens in reality. But you just got to choose a sensible number. If this is board cast in place concrete, you probably got quite a high bond strength between the pile and the soil. It's probably something approaching the soil shear strength.
Yeah. We took 67%, isn't it?
On cantilever.
Yeah, I took 67%.
Yeah.
Which
it's not crazy.
Right.
It looks, what we use on a pile, basically.
Yeah.
Alpha value.
Oh yeah.
Yeah, it's. I mean, you could apply different factors on the active and passive side. 0.5 on the active side and 0.67 on the passive side, so you could have different joints.
That's what we normally do.
So if you go to the modeler, go back to the modeler, and we select. Well, let's just go to. I just want to make sure we've got the joints, so you can define joints, joint 1 and joint 2. Say, yeah. So joint 2, we could make again material dependent. Could be 0.5. Yeah. And it's easy to then change this, because you just select your joint and say, okay. One thing I should say is we can display each liner has a positive and negative side, and we can expand them and we can show the orientations. So the negative side is on the active side of the wall.
Oh,
the positive
okay.
side, yeah. So what we can do here is structural interface properties, and on the negative side we want to assign joint 2,
Yeah.
which is the joint that we've just
So this is a little
specified
fudge thing you can do.
Right.
you know,
Yeah.
But then mainly
Point
extend
50%.
deflection
Yeah.
controls.
So
It's
now you can
fudge
see,
that Wallace
you know,
is doing because
these joints are coloured differently. We've got the structural,
But
um,
your distribution
the,
of deflection,
the liner or the
Some
beam in the
line
middle.
distribution
On the left,
rotation of the power,
we've got the
rotation of the power,
one joint, and on the right, we've got a different joint. And those joints have got different properties.
Yeah.
Yeah.
Deflection of the wall equals moment.
Yeah.
I'm just going to input that to the input.
Very complicated. It's a lot of things.
Distances on
It's we're starting to have more work like this, but it's still we still want want to try to make it work with slide, but I think you just said that it's not very good.
I don't think you're going
Slide and wall up.
be able
Yeah.
well, I mean, if you look at it, where's that slide model?
What we have. Yeah, okay.
So this is a slide model. You know, you got quite different factors of safety here,
Yeah, so
and significantly higher.
yeah.
So what's the retained height
Again, it's because the way that is affecting
on
the
top of cap?
slope, isn't it? That pile.
Yeah, I mean, all this pile is doing is shoving in at this point
Well, what it is,
a shear stress.
stiffness. So now you more like that.
So it's just putting in a horizontal load
So it's not,
onto the slice where the slip surface intercepts it.
yeah. So it's not real. What's happening in reality? You will have interaction between the element and the slide, or not the slide.
Yeah.
The slope, or how it's moving and everything. Very complicated.
And our RS pile won't do this because you've got you've got no
Sticking out.
you got this sticking up. So
Yeah. I was gonna compare those moments we had on RS2. What is my moment?
I'll send you this model so you can have a play with it.
Yeah, I just want just out of curiosity while you're here, just show you what's the moment I'm having on that depth per line. So the moment.
Is this from your wallop analysis? Yeah.
From my wallop, I'm getting 453 per meter, kilonewton meter. So it's a bit more.
Stupid numbers.
Because I'm adding a load. Oh, I'm not adding the load. So actually, wallop is it's more. In this case, it's more onerous, quite more. 50% more.
That's a lot more, isn't it?
Yeah, it's a lot more. So yeah, maybe some of the if you look at FOS, factor of safety on cohesion would be
But
1.4.
But
Yeah, they're different. Yeah.
Yeah, we didn't do the on the. So let's see if we can. What time is it? I'm just mindful. I got another meeting at 4:30, I think. So if we take so tan, let's just pick a one of these layers. So the so this material, for example, 30.4 degree friction angle. It's got a factor of safety of 0.8 on it. So this material's got a 38 degrees. Is that right?
That's 10 meters at an angle of 20 degrees. So what?
That's 38 without factor.
Yeah. So tan.
Well, that's fine. I guess it's tan, isn't it? It's tan.
8 meters, I'm guessing.
Tan 38 degrees. What was the factor again? 1.5?
1.25. 1.25.
So we can put in 18 meter long.
And then we want to say arc tan of that.
And that will educate what's going on.
Definitely based on our engineering.
600.
So
Yeah.
32.
To sell to Cadbury.
Okay, so we've undercooked.
At the minute, there's no like any testing at all.
So that friction angle, for example, should have been 32 degrees. Just for sort of time, I didn't.
Yeah. Understood. Yeah.
I just divided it all by 8. But we've got in our model we've down factored
More.
to 30.4.
So it should be giving me yeah. So it would give us better results still. Still, Wallop is going to be so far
I don't know why. No one knows.
for some reason.
Yeah, well, we would have a higher friction angle, is what I'm saying.
Yeah, that's what I mean. You will have
Yeah.
less moment in this case.
But they can still offer a small.
Possibly.
Most
I'll
definitely.
send you the model. You can run it.
Yeah. That's fine.
With the right parameters, because you've got a bit
I'll
more
play with
time.
it. I'll play with it definitely.
Have a play with it. If you run into any problems, come back.
But you said that then Wallop and obviously you said Wallop and
2.2.
and RS2 will give you the same results more or less, but not in this case, for example, because we have a slow program here. So
yeah,
it will be for something more stable, I think, than this. That's what you meant.
Well, it depends how Wallop handles the, what Wallop is good at, and where we're seeing good agreement is if we've got a horizontal surface on the active side and a horizontal surface on the passive
that's what I
side.
mean. That's what I mean.
Yeah.
So that'll be the
No.
first hole.
Yeah.
What this is in Wallop is it's a berm, basically.
Yeah, I have a berm, and it's more it's much more steep, by the way, because I allowed it to fail on that phase. So
Right.
it makes sense now that the moment is much higher. Wow, that's crazy. So that's very interesting. That's very interesting. Let me if I can have that model and I'll play with it. But
Yeah.
that was really useful.
Okay.
Yeah, 'cause it's 2 meters. Shoots 2 meters above
Cool.
the cap.
Okay, well, if you run into any problems or got any questions, just
Yeah.
give me a ring or drop me an email, and I'll do my best to help. But I've done a few jobs like this over the years, and I think the only way to tackle them properly is to do a numerical model. I used to use FLAC.
What? Sorry.
I used to use FLAC in the old days.
You discussed that in the FLAC. I didn't know what was that FLAC. Interesting.
Yeah, it's another product, but it's a lot more complicated to use than RS2. So for routine work, I wouldn't sort of recommend it. I think RS2 is far more user friendly. But it's a good tool for, even if you just got a basic slope analysis, to check the results of Slide. If you didn't have to plug a wall into it, it's dead easy. You can just drag and drop your Slide2 model into RS2 and click run. Seeing it demonstrated, it gets a little bit more time. It takes a bit longer to set the model up if you've got to install a wall, but
it's not too difficult.
Oh yeah.
It's not. It's the first time you do it, it'll probably take you half a day or something. But once you've done it once or twice, you can do it in an hour or so.
Yeah, absolutely.
Second hole.
Okay.
And that time could probably be saved in the time you spend iterating between different programs. And I would say also there's less uncertainty, because taking results out of one program, feeding them into another, both programs have got inherent assumptions and simplifications.
What distance is that?
Where are you left at the end of the day?
Yeah.
This I think is one model, one analysis. It gives you, is it stable? Does it satisfy Eurocode 7 design requirements? And what are the moments then? And what are the shear forces in the wall? It'll also give you an indication of wall deflections as well. So, one of the things
1.5 below that.
We can plot on this. There's a whole bunch of stuff we can plot. So show values. We can look at horizontal displacement of the wall, for example. So we're seeing 57 millimeters, I think. This low case, actually, this is the failed thing. Yeah, so we're seeing 14 centimeters of deflection at the top of the wall.
Yeah, so it's quite a lot.
Yeah. But that'll depend on soil and wall stiffness.
Hello. You okay? Yes.
What else can we look at? We can look at things like we can show which joints have failed. So if we so these red joints, you can see these joints have gone red now. That's indicating that we've got failure in the joints. We can look at let's say normal pressures. Show joint normal stress, and we want to look at the negative side, which is on the active side.
Yeah.
Okay. So we can look at joint normal stress values. We can look at the same. So this is, if you like, the pressure on the wall.
Is it? Okay.
Show values, joint normal stress again, but we'll look at the positive side
And that
and
second,
the passive side.
And the holes are then 1.5 meter space.
Yeah.
Okay. So you've got much higher pressures on the.
Makes sense.
Sam
Yeah.
sent an email explaining it. Calcray basically
So, yeah.
know about it, and they're going to change their platform.
Well, so thank you for that. There was a lot to take in, but it was quite clear, to be honest. It's very interesting. I'll have a play with that, and I probably will come back to you. But yeah, thank you very much, Ian. It's good.
Yeah, no problem. As I say, and I'll send you the model, and then if you want to sort of pick it up or have any questions, we can we can have another call or whatever. Okay.
Perfect. Thank you very much. Yeah.
Lovely. Okay.
You have
Thank
a
you.
Nice evening. Thank you very much.
Yeah. You too.
Take
Cheers.
care,
Bye-bye.
Bye.
Bye.
Bye.